Okay, Sophia, shall we start?
As you want, Kiyotaka.
Yes, please.
Right. So today we have the third event of the Q2XAFS 2024, organized by Kiyotaka. And this time we have Diego Gianolio as our speaker from Diamond Light Source. And Diego is going to present the discussions and the findings, so a summary of all the meetings that the working group that had as a task to work in tender X-ray spectroscopy have been having during the last few months. Diego will give the presentation. If people have questions, I will advise to put it in the chat. I am happy for people to ask a question live. I think it's much easier, but I don't have everybody in my screen, so I cannot see who is asking questions. So if you put it in the chat, then I can call your name and you can ask the question live. If there are a lot of questions, we can make a break in the middle of the talk and then we can go through them. And if not, we can wait until Diego finishes the presentation. So Diego, the floor is yours. And yeah, thank you so much for giving the talk.
Thank you, Sophia, for the introduction. So yeah, as Sophia mentioned, I'm here to present the findings of this working group that we have done on tender X-ray spectroscopy. I would start maybe changing the normal order when the acknowledgements are at the end to thank all the people that contributed both with their presence in the working group and writing the report and sending me contributions for this presentation, including Itoshi, Giovanni, Simon, Montana, Alexei, and Delphine. So in the working group, so we had several meetings with a good participation. People were selected based on who expressed their interest in the previous Q2XAFS workshop held in Melbourne in 2023. But if there are more people in the audience that are then interested to give contribution, please contact us and we are happy to include you in the work that is still to be done. As you see here, there is a list of topics that we discussed during our working group. We started from the definition of the tender energy range, and then we discussed a bit more technical details, checking what beam lengths are available and what are the technical specifications, how to do the energy calibration and energy resolution that is important from the scientists working in these beam lines. And then we discussed a bit more on things that could be of interest for the users and how to give them information and guidelines, such as for sample preparations, what are the challenges, what are the best methods, acquisition modes, what sample environments are available, other complementary techniques that could be used for characterization, optimization of the data collection, how we can do it in the best possible way to get a good signal, since we are talking about quality of the XAFS, and then data treatment and data analysis, how to treat the data properly, and then two major challenges that are self-absorption and radiation damage. And in the end, we try to draw some conclusion and collect a list of the needs and recommendations that we have. So I will start from the definition, because the tender energy range, it's always been in a bit of a gray area between the soft and the hard X-rays. So there is an overlap between these regions, and it's very hard to define like precise limits on where the soft ends, where the tender starts, and also where the tender ends and the hard X start. So we came up with two possible definitions. One that is more technical, based on the limitation of the data collection, and another one that I will call experimental, that maybe it's easier to understand for the users. So for the technical definition, we were suggesting that the lower limit should be defined, but the energy that can be reached using double crystal monochromator instead of gratings that are more commonly used for soft X-ray beamlines. And here again, like there are still different possibilities because there are different materials that can be used for the monochromator. So if we just limit ourselves to the silicon 111, then the lower limit would be at 2 keVs. But there are several beamlines that use other materials, such as KTP, potassium titanyl phosphate, or beryllium aluminum silicate. And in this case, we can push the lower limit down to 0.8 keV. While for the high limit, we all agree that normally like hard X-ray measurements are done in air, but tender X-ray measurements are normally done in a controlled atmosphere. So the real limitation is how long can be the path of X-rays in air. And so considering a round number that is 10 centimeters, this limit would set the energy around 3.9 keVs. The experimental definition is more based on the quality of the data that we can obtain. So when you go to soft X-ray, normally you collect very short XAFS or XAFS, as they are more commonly called for soft. While if you are in hard X-rays, you are normally interested in collecting longer energy range and get a good XAFS. So if we base this definition on where we can measure something that is more than just a very short XAFS, then we can have as two limits the magnesium KH and the calcium KH. So this would be between 1.3 and 4.2 keV, which is very similar to the other technical definition. And we think that this would be a definition that would be more practical and easier for the users to understand. So in terms of beamlines availability, we created a table with the technical specifications of the beamline based on the people that were participating to the group. So clearly this is a non-exhaustive list. We know that there are other beamlines that can measure in the tender X-ray range, and we are happy to include them again, like if you send us the information. But in general, this is was meant to show what is the availability, what type of energy range we can cover, beam size, and other specification. And as you can notice, there are a few beamlines that can push more towards the lower limit, so they are more focused in the soft or tender, and other beamlines that maybe are more dedicated to hard X-rays, but they have also the possibility to collect the tender X-ray spectroscopy data. And also in terms of beam size, there is a good variety. There are some beamlines that have a micro beam, so they also allow the possibility of doing some mapping, fluorescence experiment, and others that instead have a very wide beam that might be useful to overcome inhomogeneities of the sample and give a bit more stability and collect a good XAFS. So one of the first things that we discussed that is a common problem, I think, for everyone working in the beamlines, but also for the users when they want to compare their data to data collected in another beamline, is the energy calibration. So this is clearly important at every energy, also in the hard or soft X-ray. But probably for the tender, we have a few more challenges. Like while for the hard X-rays, if you have a metal, there is a tabulated value where you know that the edge position should be, and there are many metallic foils available. In the tender region is more difficult to find elemental samples. And so sometimes the calibration is done for beamlines that have both the possibility of measuring at tender and hard X-rays, is done at the lowest hard X-ray possible energy, and then we just move the monochromator and assume that the calibration is maintained. Or we can collect, for example, sulfur, elemental sulfur that is available in powder, where again the edge is tabulated. But we all thought that it would be useful to have a table with materials that are commonly available with their edge position that is then can be then used by any beamline everywhere in the world, where we have this booklet that reports the position of the edge, and we all use this position to calibrate our beamline. So we try to collect some information here. There is a first draft of the table where some of the the references are foils, so we take the reference from Hephaestus or from the X-ray data booklet, and some others are oxides or chlorides or different type of mixed oxides, where the position has been taken by doing a measurement of the foil and then immediately after the measurement of this material. So it's been calibrated to another energy and then measured. So we think this could be a starting point with the hope of populating this table more and more, and also make the calibration more consistent across beamlines. Another problem that we think is maybe even more important in the tender X-ray range than in the hard X-ray is the energy resolution. As you probably know, the core hole broadening that we have at hard X-ray is much smaller at the tender X-rays, for the tender X-ray edges. So when you want to compare spectra collected at different beamlines, it's important to be aware of what the energy resolution is. There are different ways to measure the energy resolution. One way is to rely on the intrinsic bandwidth of the crystal that has been used for the monochromator, and then eventually correct it for a residual divergence of the incident beam on the monochromator. For beamlines that have the possibility of reading the angular position of the monochromator with an encoder, then one can actually measure it by doing a rocking curve, so scanning the relative angle of the second crystal with respect to the first. And if this is not possible, there is other ways to possibly determine the energy resolution by measuring the width of a white line peak. Here you see, for example, the peak of argon gas, and by doing a peak fitting of the white line, one can determine the full width arc maximum and then derivate the energy resolution of the beamline. And after these more technical issues, we try to focus more on what could be interesting for the users and what type of guidelines we can give them. So we discussed the sample preparations, and we found out that, of course, there are challenges. Some of them are similar to the preparation that you need to do for hard X-ray beamlines, and others are a bit more unique issues that are more common only for the tender X-rays range. So some of the similar challenges is to be able to get a good signal to noise from the sample. And this means making sure that the sample is homogeneous, that the sample is not changing while we measure it, so preventing the beam damage, that the thickness of the sample is optimized, and that there are no pinholes that could cause artifacts, and ensure stability and reproducibility. Other issues that are more unique due to the fact that we have a lower energy, a consequence is, for example, that the penetration depth of the X-rays into the sample is lower. And this causes multiple issues. One is that the ideal thickness of the sample is much smaller. And then it makes it difficult to prepare very thin samples that can be still mounted on the beamlines. And of course, there is also the problem of self-absorption. When you cannot make thin samples, it would affect the quality of the data. I will talk more in detail about self-absorption later on, so I won't spend too much time now. Then another problem is that when you prepare pellets for hard X-rays, the common procedure is to dilute the sample with boron nitride or cellulose. But for tender X-rays, also the dilutant material starts to be absorbing. And so you can use only a very small amount, and you need to be careful about what material is used. And not only about the dilutant, there is the need to be careful about any material that is used for the sample preparation, since they could contain some of the elements that have an edge in the tender X-ray range. So it is very important to study the composition of tapes, windows, or any material that is really used for the sample preparation. Another issue would be to measure air-sensitive samples. while for hard X-rays it's easier to enclose them into a cell or into some packages. Here they can be sandwiched, but they should be sandwiched between very thin films, or possibly transferred directly from the glove box or where the samples are prepared into the chamber where the sample is measured, with the need of dedicated transfer systems. Another issue could be the sample holder, because as well they could contain some of the elements that you want to measure, or that will have edges in the energy range of interest. So we found out that we have between beamlines more or less common methods for preparation, although these methods could change depending on different energies within the tender energy range. So if we go towards the lower energies, it is very hard to measure sample in transmission because the ideal thickness is even lower. And sample could be prepared as a dust that just adheres electrostatically to a thin window. Or in case of preparation of a pellet, it's very important to use ultra pure materials like cellulose or glucose, and also in very small amounts. Moving higher up in energy, it is possible to deposit a bit more of samples. So a common procedure would be to spread the powder on a thin layer of tape and then remove the powder in excess. Or sample could be suspended in a solution and then dried on cellulose or coffee filters. And there is also the possibility already to measure some liquid samples, but always using very thin windows and with an O-ring or the possibility to adjust the thickness to a very small amount. Moving to even higher energies, then all the methods that I previously described could be used, but it is also possible to start preparing thin pellets and using methods that are more common for hard X-rays. And in terms of data acquisition, most of the tender X-ray beamlines will have an experimental chamber where the sample is measured in controlled atmosphere. This is due to the fact that, as we said before, like it is very hard to measure in air due to the air absorption. So we cannot work in ambient atmosphere. We need an experimental chamber. Here on the bottom right, you can see a picture from Lucia beamline of one of the inside of one of the chambers with a sample that is mounted and the X-rays that can go in and out. And then again, we have the possibility of different acquisition modes. One would be a transmission mode that is much more challenging than for hard X-rays because, as I said, the sample need to be very thin, and also the ion chambers need to be maintained in some controlled atmosphere, possibly with low pressures, to avoid having windows and then keeping them at the same pressure of the chamber. Fluorescence mode is a common mode for acquisition, but more frequently than for hard X-rays, you will end up with the case of thick and concentrated samples, just because the definition of thick will now change. And for this, there are ways to minimize the problem of a thick and concentrated sample. That could be, for example, self-absorption effects by measuring, for example, ingress exit geometry. Another acquisition mode that is less commonly used in hard X-rays, but may be more commonly in soft X-rays, is to measure total electron yield. This is possible if the samples are slightly conductive, and in general, the samples are then mounted in contact with the indium or aluminum plate or a carbon tape to improve the conductivity and being able to measure the current coming out of the sample as a result of the X-ray excitation. And there are also methods to increase the signal by using a partial helium atmosphere in the chamber that gives a better conversion yield. So I don't know if we have questions, otherwise I will continue from here. This is a good moment to interrupt.
Yeah, Diego, there is no questions in the chat. So just a reminder that please put your questions in the chat, and then at the end you can ask them live. But because there is no questions, I think we continue, Diego?
Yeah, okay, yeah, good to go. So, of course, like apart from the sample preparation, it is, I think, nowadays more and more common that we want to study materials that are developing, so under reaction conditions. And for this, for hard X-ray, there is a wide range of sample environments available. For tender X-ray region, the development of sample environment is again more challenging. One, again, for the same reason that I explained before, so that all the materials that you are using that could intercept the beam would affect the measurement. So the windows need to be thin, and they need to not contain any element that could be in the energy range of interest. Uh, Discussing with the other people in the group that work in tender X-ray beamlines, we came across to, well, I think that the two most common sample environments are ovens and cryostats that allow for temperature-dependent studies. And in the case of cryostat, they also help with beam damage mitigation. There is a variety of these sample environments that allow both to measure pellets or measure powders in capillaries, of course, again, very thin. While also for cooling down, there are different methods. There are helium or liquid nitrogen sticks, where the temperature can be controlled both by controlling the flow of the nitrogen or helium, or by heating with some resistance, so going down to base temperature and then heating towards room temperature. But it is true that there is, we all recognize that there is an increase in demand from the user community for specific sample environments in order to study reactions and being able to overcome the difficulties of working in this controlled atmosphere. So there is already some sample environments that have been developed, liquid cells that I mentioned before with thin windows, but also some cells that allow for flowing liquids, so microfluidic chips, for example, cells that where you can perform electrochemical experiments, again with liquid flowing, or battery cycling. And this would also need electrical connections that are going into the chamber so that the potential can be applied to cycle the battery. And some of them allow not only just transmission of fluorescence measurement, but also mapping, so with a bigger window. And then there is a few catalytic reactors that allow to study the system under pressure or temperature. And then apart from the sample environments, there is also interest in using other complementary techniques for the characterization of the samples. So here I included a few cases. So the first two represent techniques that could be potentially used simultaneously and that give complementary information. For example, we all know that XAFS and XRD are they complement very well, because XAFS gives information more on the amorphous part of the sample, while XRD will give information on the crystalline part. For tender X-rays, there is a complication from the fact that if you want to measure XRD, normally we do measure in transmission through the sample in hard X-rays, but for tender it's hard to go through. So there is a possibility to put the detector in a backscattering geometry, so putting it in front of the sample where the beam comes from. But again, you need to consider that working in this controlled atmosphere chamber, there is not much room to fit a diffraction detector in there. And then the other problem is that if you want to measure XRD in transmission through the sample, ideally it would be easier to do it going at higher energy. And so you would move to a higher energy to collect the XRD and then move again to the lower energy in the tender X-ray range to collect XAFS, but in this case it wouldn't be simultaneous. Other characterization techniques that are commonly combined with XAFS and that are very well complementary are the vibrational spectroscopy, so infrared and Raman. Again, it is challenging to integrate a probe that will be able to go inside the sample chamber while maintaining the vacuum or helium condition, but it has been proved that it's feasible, and it looks to us that is a very promising approach for the near future. And a few beamlines already have the possibility to collect Raman and XAFS simultaneously. The other techniques mentioned here are more techniques to characterize the sample, possibly prior to the measurements, in order to optimize the measurement conditions. So, for example, SEM, ICP, and IMS can provide a rough or precise elemental composition. It would be useful to assess also the sample uniformity, grain size, defects, and this will surely help in setting the XAFS acquisition parameters. In particular, if you then want to do a mapping of the sample, then you could do first have an overview with one of these techniques and then go into a more specific point with the tender X-ray beam. And well, of course, like microscope and X-ray cameras are also very important, especially when you work inside the chamber and you might not have access to see how the sample looks like, or if you are properly aligned. So they will be important for sample alignment, for spot selection, and to monitor the X-ray cameras, also to monitor sample homogeneity if there is any beam transmitted through the sample. And then there are other instruments that could be useful to use in combination with the X-ray absorption measurement, in particular for in situ and operando experiments. So a mass spectrometer if you're doing a catalysis experiment, or potentiostat if you're doing an electrochemistry or battery experiment. Then moving towards the data acquisition and data analysis, of course, there are several parameters to optimize for the data collection to get a good quality of the data. One thing to take into account is that the energy range when you measure in tender X-rays could be much shorter than what users that are commonly using hard X-rays are used to. And this could be limited by changes in the background, by other edges from that are in the same range from other elements. And in this case, like, there are a lot of edges if you are talking about L or M edges, and they are much closer to each other. And sometimes like the energy range is just limited by the fact that we cannot reduce the noise, and then the signal to noise will not improve anymore. And by the time resolution as well, but I will discuss this just shortly later. So normally, like, the pre-edge is a bit shorter than for hard X-rays, again due to the acquisition time needed. So 50 to 100 dBs are normally sufficient to subtract the baseline, and the maximum energy is again much shorter, but our suggestion would be always to collect at least 200 dBs in order to help then the data treatment, in particular the normalization of the data. It is true that most of the times only the XAFS is needed, or a short XAFS, but it's true that a short XAFS can be collected, as we said, for the edges between silicon and calcium. And in terms of time resolution, we need to consider that when we work with DCM, normally to reach these energies, we are working at very high angles. So this means that if we have a limited speed for the scan of the monochromator, more time is needed to perform physically the scan. And working in a region where air or any other windows could absorb, the signal to noise is expected to be lower. So there are different ways to collect the data. As for hard X-rays, the most common probably in this for tender is still the step scan, where normally 1 second per step results in a total scan time of 10 to 15 minutes if you collect a short XAFS, or 20 to 30 minutes if you measure an XAFS. It is also possible to do a continuous on-the-fly scan, with a total scan time that could range between 3 and 5 minutes. But here again, it is likely that you need multiple repetitions to improve the signal to noise. And once the data have been collected, the data treatment and analysis also present some unique challenges. One that I mentioned before is that normally the spectra are quite short, so it is difficult to do normalization. The other is that because of the short penetration depth, while scanning in energy, you could also have a change in the penetration depth as a function of energy, and this could affect the background. And there is also the possibility of presence of some sort of long period oscillations. So in this case, like it is possible to do the analysis with the common tools like Athena and emitter tools, but having a very short range, sometimes people need to spend a lot of time in picking up the points for the pre-edge and post-edge so that the lines are well aligned. And many people that are working with tender X-rays tend to develop their own custom-made scripts in order to have a normalization that is adapted to the signals that they collected. Of course, as for any other data analysis, if any error is made during the data reduction, this could introduce artifacts and systematic errors and then lead to a mistaken interpretation of the results. So it's very important to be able to do this properly and to provide the right tools to the community of users. When talking about the analysis, the problem of having multiple edges becomes, of course, very important because, again, it shortens the range and doesn't allow to do to have a good Fourier transform, for example, for the XAFS. There are also other interferences that could be coming from gas left in the chamber, for example, argon. And there could be artifacts that are introduced by these nonlinear backgrounds that could be coming from the fluorescence or the total electron yield, for example. So it is very hard to have a reliable quantitative analysis, and most commonly people use a qualitative analysis using a fingerprint approach. But this is still problematic because we really need to have some reliable spectra of reference samples where you don't only have the shape of the sample, but you are sure that the energy calibration has been applied properly, that the data have been normalized, and that there is no issue, for example, due to the self-absorption that could affect the intensity of the signal. And then we need to still be aware that samples that have different particle sizes or different concentrations that could be the same reference sample, but they could have different spectra. And so this could affect the results of the analysis. And so one of the main problems that I mentioned multiple times in this presentation is really the self-absorption. So self-absorption appears because of, as I said, the change of the penetration depth of the X-rays as a function of the energy during the scan. And this could affect the amplitude both of the exchange features of the XAFS oscillations in a nonlinear way. So of course there are mitigations. There are ways to try and avoid it in the data collection, so doing it experimentally, or at least minimize it by diluting the sample in a light matrix, or maximizing the angle between the sample and the incoming beam, so measuring more in grazing geometry. But there are limitations. Sometimes the samples cannot be diluted, or the sample environments doesn't allow you to rotate it in grazing incidence. So sometimes it's just not possible to prevent the presence of self-absorption. And theory can help us in correcting the data. So there are algorithms available to correct these changes in intensity in the spectra. But these algorithms normally require the exact chemical composition and an accurate measure of the angle of incidence. And this the combination of these two information is very hard to achieve, because if we know exactly how the material is, we probably don't need to do the spectroscopy, and the angle of incidence is very hard to measure. So there are other ways to correct. A common procedure is to try and measure the sample, for example, with two different acquisition modes. Self-absorption is present more commonly in fluorescence. So if there is the possibility to also measure in transmission or in total electron yield, then the two spectra could be compared, and the correction parameters for the self-absorption could be, let's say, tuned in order that the two spectra match. The spectra collected with the two different acquisition modes match between each other. And if this is done for one reference material that has a well-known composition, you can also then reapply the same correction parameters to other samples. Of course, taking into account that the sample preparation might be slightly different. If this correction is not possible, between the group, I think we agreed that it's probably better not to try and modify the data just to make them look good. Because the risk of introducing artifacts and not obtaining the right result is very high. So it is probably better to discuss trends in the data evolution. For example, if you're following the reaction of a sample or a sample as a function of temperature, without relying on the absolute intensities. Another challenge that we have noticed in the tender X-ray being more commonly present than in hard X-ray is the radiation damage. I know that we already listened to the second talk of this series of Q2XAFS that was focused exactly on this, on beam damage in X-ray absorption spectroscopy. So I will not spend too much time on just saying the findings that we had for the tender X-ray part. So we know that, for example, this happens more often. It's frequently observed in the tender X-ray region due to the stronger interaction of the X-rays with the material. It shows as a change in the spectra. So if measuring multiple repetitions on the same sample, you can see changes in the intensity of the white line or position of the energy. The type of damage could be reduction or oxidation or other type of physical chemical changes. And normally we think that it affects more frequently samples that contain organic components. And another thing that has been observed, since we sometimes do measurements in a controlled atmosphere, is that the presence of water could play a role. And this could be water inside the sample or water in the atmosphere that you're using to do the measurement. And so how can we estimate it? Well, normally you monitor the changes of the intensity of some peak or feature over time, possibly staying at a fixed energy to have a better energy resolution and not having to repeat the whole scan. And mitigations would be common mitigation that can be used also for hard X-rays, such as cooling samples to cryogenic temperatures, reduce the intensity, the flux of the beam, measure different points across the sample. And one finding that I think it was due to some specific preparation for the tender X-rays was to embed sampling resin sometimes can help, maybe to prevent, for example, contact with water in the atmosphere. So, reaching the final slide, I would say to try and draw some summary in conclusion. For the energy calibration, we think that what would be really useful would be to have a specific booklet for tender X-rays where we collect as many as possible spectra of common reference samples, where we don't only have the position of the edge that can be used for calibration, but also position of the following peaks, for example. For the sample preparation, we are thinking to collect the methods that I presented today and more, if possible, into some clear instructions that we can then provide to our user community, pointing out the best possible sample preparation, and also a list of the clean materials that can be used, for example, for tapes or windows. For sample environments, I think we agree that we need to continue developing new setups, in particular for the in situ and operando experiments, because we recognize that there is an increase in demand, and it would be useful to share the information and the design through the different beamlines that work in this range, so that we can grow faster, let's say, in this design. And then for the data analysis, we surely need a database. There will be another working group following this one. Sorry, another talk on Q2XAFS following this one, talking about databases. We might need even more information for the tender X-ray range, because for us it's very important to have as reference spectra in this database data that have been properly normalized, where we know exactly the height of the white line and of the other features, and then we can exclude any self-absorption or data treatment problem. And then possibly some dedicated software package or tools that can be added to the software packages already available that can take into account the difficulty in having short pre-edge ranges or background that change in a non-linear way. And with this, I think I finished my presentation, so I'm open to questions and discussion.
Thank you so much, Diego. Thank you for this very comprehensive talk, and also thank you to the working group. I mean, you have done a fantastic job, I think, identifying well, a lot of the challenges that we can find when we do experiment with tender X-rays. So at the moment we have a question from Gianolio. And Gianolio, you want to ask your question live?
Yeah, but I can. Yes, I can see. Probably Diego has already answered in a good part. My question was coming in. So linearity in this data set in particular regarding the amplitudes clearly is tricky because you can have a lot of effects. I mean, self-absorption, you definitely mentioned that. But from my experience as well, when you measure in total yield, if your sample is not particularly conductive, the response tend not to, go up as quickly as you would like it. So linear combination is tricky. And again, the proposal was, is there any interested to share references? So, we can use as well. And everybody can use, users can use, to check that the standards they are acquiring are usable or not. Or is there any interest in giving indication about how to measure, I don't know, in total electron yield as well? That one can be tricky. My experience, again, if the pressure of the gas is too high and the voltage of polarization is not high enough, your response is equivalent to have a self-absorption. So yes, I think you answered it.
Yeah, I mean, as we said, like when we recognize that there is there is a challenge here. And yes, of course, we are very interested in having a database, making sure as much as we can that the quality of the data and that the data are acquired in the best possible way. So it would be useful, for example, like to do test measuring materials. One thing that was discussed that I didn't mention in the talk was to try and measure, for example, the same material but prepared in different ways and see how the preparation could affect the signal, and in particular this intensity of the white line. Like, is the dilution sufficient, or should we also measure the dimension of the grains, because there could still be a local self-absorption that you don't take into account.
Okay, thank you. There is another question from Matt. Matt, do you want to ask live?
Yeah, hi, can you hear me? If you can hear me, I was
Yes.
happy. Yeah, hi, Diego, great talk.
Hi.
You talked about energy calibration and resolution measurements also, and I guess I would like to hear a little bit more on what would help the most with that. So if we could determine the positions of some of those edges well, would that be what you want published, or do you want reference spectra in a database? how would you like to see
Yeah.
calibration and resolution presented?
I mean, I think there are different levels, right? So the first level is to have a table with the edge position, and that's the minimum I think that we should have. Possibly not only the one of the elemental sample, but also some of the salts that are easy to buy, so that everyone can have it at their beamline. And then the second level would be to have also the reference spectrum, so that we can all define the edge position in the same spot.
Right.
And
Okay.
also to confirm that there are no distortions, for example, because sometimes, like, if the intensity is very low, you could pick the energy position in a slightly wrong energy. So yeah, I would say, first of all, yeah, publish a table of energy position, and then if we can go forward and have a full database with not only the edge position but also the shape of the spectrum, it would be ideal.
Okay, that's helpful. Thanks. I've been thinking about how to do these things, and
Yeah.
so that's helpful. Thanks. Yeah.
And probably also, since you also mentioned the energy resolution, it would be important to, if we collect database, to refer to have as a metadata the crystal that has been used, or the energy resolution measured in one of the ways that I mentioned.
Sure. I guess for resolution, one of the things that might be challenging is to see how one could reproduce that at multiple beam lines and see how
Yeah.
consistent that is.
Yeah. But for example, if
Right.
the beamlines have the possibility to do a rocking curve, it could be
Right.
useful to link the rocking curve to the
Right.
spectra, for example.
Sure. Yeah. Yep. Okay. Great. Thank you.
Yes.
Thank you so much. So now that Matt is in the call, you also mentioned about the difficulty analyzing the data and the background and things like that. So how do you think we can improve that, and what we need? I mean, clearly the help from people like Matt and Bruce and all the helpful, fantastic scientists that are coding. But what do you think specifically we need?
So I think, well, we will try to collect in our report a list of specifications needed, yeah. But I think that three major problems that I can see are, the first one is having a very short pre-edge range. So I think now with large or with the code, there is more options to modify this, the way the pre-edge is extracted. But for example, I remember in Athena, you have a straight line but not a constant, and sometimes it's just easier to have a constant value to remove as a background, because I remember playing with the points of the pre-edge start and end to have a flat line. And that's a very simple thing to do, probably having the zero order available. For the background in the post-edge, that's more complicated, because we really would need to understand in a better way why the background is changing. We see very often curved background that can be extracted with the polynomial function, but sometimes we have, as I said, even oscillations in the background, and that's challenging to do with the polynomial functions available. And then the other tool that could be useful, I think, it would be a way to do this self-absorption correction in terms of comparing two spectra. So if I know that one spectrum is good and I have another one on the same material collected in fluorescence, can I do a normalization of a spectrum with respect to another instead of doing a normalization, a standalone normalization? And I'm not sure how this can be implemented in the code, but it would be something maybe useful. So let's say an empirical normalization, if you want to call it like that.
So Diego, when you're in the working group, you had this list of, a wish list of things that you can help. Do you already have that? You discussed?
Well, we discussed something. I think the exact points we might need to have a bit more conversation on what we really want, because what we said is that every one of us has its own code to do the analysis, and that we wanted maybe to share it between ourselves so that at least is available. Or, as we say, we could share it with Matt or other people that develop the Athena codes.
Okay. Okay.
And
No,
Matt.
this is there is another question in the chat from Donato. Donato, do you want to ask your question live?
Yeah, sure. I was back to the point of self-absorption and background correction. Could we use, especially considering that as we go lower in energy, the more these approaches to finite states, it's easier to. It should be. Can we model using computation the background and the self-absorption correction in order to help interpret our data better? That was more my point.
Okay. Well, I would say, so for the background, it would be difficult to model with theory because there are really some sort of systematic errors due to the measurement. And those are hard to model, I guess. For the self-absorption correction, we have methods to do it. We have equations, but again, the problem was more the knowledge that we have on the sample on the exact conditions on how the spectra was acquired. But I think this question might help me raising a point that I might have overlooked. That is the fact that we really need good theoretical support, as for the hard X-rays, is very important, and in particular in this region where you have a very short sense, having a good theory and an easy way to try and see how the spectra should look like. So if that was maybe more the point of your question, Donato, that yes would help a lot. I know there are already methods, but it's always, I don't think we are still at the level where we can use the theory to normalize the experimental data to it. But really, theory is a key, is maybe even more important than for hard X-rays to be able to simulate xenes and know maybe what relative intensity we expect between features.
So Diego, if I understanding, you want a round robin for tenderes, right? You want a database for tenderes, right? You want.
I mean, we want everything, of course.
No, and it's perfect. I think it's fantastic. But I mean, just a little bit of a funny question. But you started your presentation saying it's very difficult to identify the tender regime. I mean, it's not soft, it's not hard, it's something in the middle. There are lines that do soft and tender. There are lines that do tender and hard. So how do you think we can increase, well, the actually interaction or the engagement with the, the soft and the, oh my God, the soft and the hard?
Yeah, no, this is very important, and I think, as I said, like for the tender, we sometimes use some methods from the soft and some methods for the hard. But it is true that some of the problems that we still have on the tender, like for example, I would say the sample environments. Many sample environments that are used for soft X-rays will be surely also a good option to use in the tender X-rays. And as you said, maybe the interaction is not that much. I come more from a hard X-ray type of background, to be fair, but probably having I mean, some joint meeting with the soft X-ray community. I don't know how many people, for example, are present to this meeting of the soft X-ray community, but it would be very good to involve them or to have some common workshops where we can exchange ideas.
So maybe Kiyotaka, this is something that we should think about for the future.
Yeah, I think so. Well,
Yeah.
it's, interaction is important between
Yeah.
the soft and yes.
And if I can ask another question, just are you guys, I mean the working group, planning to write some, like report or guidelines or something that people can use and refer to?
Yeah, so we already started putting together a report based on the meetings that we had. It is still in preparation, let's say, where there will be all the information that has been presented today, and even more. We have comparison, for example, of data collected in different beamlines. So there will be a part that is maybe more. I think we can come out with two different documents. One that is more a report with all the information, technical information as well for us. And I think it would be useful also to come up with instead something more for users. So just a list of guidelines of what is available, for example, which are the beamlines, what is the range that we can cover, what are the type of experiments that can be done, sample environments, as I said, and guidelines on the best sample preparation and best data analysis and treatment.
So referring to the analysis, Matt very kindly saying that any recommendation or ideas for doing normalization or self-absorption correction, they will be happy to add to tender specific.
We will try to
Thank you
see
so
what
much,
is the
Matt.
best way.
Thank you so much, Matt.
Thank you, Matt.
Okay, so I think there is no more questions. So I think Kiyotaka is now back to you.
Yes, thank you very much, Diego and Sophia. It's very nice talk and nice discussion. And I finished today's conference.